This video will look at using and understanding transition matrices as well as calculating basic state matrices. So our first example here is from the VCAR 2017 paper. It's from paper 2, so that's the extended response, and it's a slightly adapted version of question 2 out of that exam. So junior school students at this school must choose one elective activity in each of the 4 terms in 2018. Students can choose from the areas of performance, sport and technology. The transition diagram below shows the way in which junior students are expected to change their choice of elective from term to term. So what this is telling us, remember, each of those vertices, the points, is a location, or in this case is one of the subject areas. So we can see here P for performance, that it is expected that of the students who choose performance in one term, 40% will choose that performance again. Another 40% will move and choose sport, and 20% will move and choose technology. And so that's the same for the other 2 as well. So of the students who choose sport, 60% are expected to choose sport again the following term, 20% are expected to choose performance, 20% are expected to change and choose technology. Finally, technology, 60% will choose technology again the following term, 20% will move to sport, and 20% will move to performance. And so generally speaking, we start off with a really easy question, just interpreting the transition matrix. So of the junior students who choose performance in one term, what percentage are expected to choose sport the next term? So we're asking for the percentage moving from performance to sport, and so we can see that that would be 40% would be expected to make that change. Matrix J1 lists the number of junior students who will be in each elective activity in term 1. So we can see there the rows are labelled to match the electives. So P for performance, S for sport, T for technology. So part B is asking us 306 junior students are expected to choose sport in term 2. Complete the calculation below to show this. So what we're wanting to do is identify, using the percentages from the diagram above and the number of students for each elective in term 1, show that calculation to get the total of 306 students to choose sport in term 2. So if we go back to the diagram, what we're actually looking for is all of these values coming in to sport. So firstly, we were told there were 300 students in performance, and so 300 students, of which 40% are going to change to sport. Okay, so we've got our 40% of those 300 will end up in sport. Then if we think about the percentage that will move from technology to sport, and so we had 20% will move, and there were 210 students in technology into term 1. Sport, we were told there were 240 students in sport in term 1. 60% of those will remain in sport. So 60% of the 240 students will remain in sport. And so that's the calculation that we need to do to hopefully arrive at 306 students total. And so when we're doing those calculations, a reminder, we're changing those percentages into decimals. So 40% is 40 over 100, or 0.040. The 240 represents from sport, and we said there were 60%. And the 210 from technology, we had 20%. And so when we put those values in our calculator to double check, we end up with that total of 306. Part C, we've got of the 300 students who chose to performance in term 1, how many are expected to have remained in performance by term 3? So again, if we just quickly refer back to our diagram, what we're asking is this of this 300, who is going to remain? So after one term, so from term 1 to term 2, we're going to have 40% of 300 will remain. And so 40% of 300 is 120. And then from term 2 to term 3, again, 40% will remain. And there were 120 who originally remained from that first 300 students. And so 0.4 times 120 gives us 48 students remaining. So if we were to write that as one calculation, we could do that as 0.4 times 300, and then 40% of that again would give us 48 students remaining. So we now look at calculating any state using recursion. So much like we used recursion in finance, we need an initial starting point, and we call that our initial state matrix. So that column matrix, which is telling us the numbers or the population at each of those locations at the beginning. And then our recurrence relation, we're using our transition times the state to get what's happening in the following state. So whether that is after 1 year, 1 day, 1 month, depending on the scenario. So each of those calculations, every time we move once through that transition diagram, everyone moves once. That shows us the number at each location after one transition. Okay, and that would be S1. If it was S3, that would be after 3 transitions or 3 loops through, 3 sets of movement through that transition diagram. So our first example here, we have an airline parks all of its planes at Sydney Airport or Melbourne Airport overnight. And the transition diagram below shows the change in location of these planes from night to night. It's also represented in the matrix T, so we're given it in both formats. So we can see here that 80% of the planes that were parked at Melbourne one night will remain parked at Melbourne the following night, whereas 20% will change location to Sydney. Of the planes parked at Sydney on a particular night, 52% will remain at Sydney the following night, whereas 48% will change location to Melbourne. And so it's important to feel comfortable with interpreting what's happening there in the diagram. Our transition matrix here, whilst our columns are not labelled, we can see Melbourne to Melbourne is that 80%. And so we're going to label in that direction, I guess. And remember, with our transition matrix, we read down and then out to the right. So that's the flow of the movement. We're moving from and to. Okay, so this question is saying, on a Monday, there are 60 planes parked at Melbourne Airport and 35 planes parked at Sydney Airport. And we want to represent this information initially as our initial matrix S0. And so that's just a case of putting that information into our matrix here. We do want to make sure that we're following the same order of the labeling that we did in the transition matrix. So 60 planes at Melbourne, 35 planes at Sydney. And just note, in case you have missed that, we did change that value for the Sydney planes when we were working through this question. So just make sure you're using that 35. The state matrix describing the number of planes expected to be parked at each location after n days after midnight, Monday night is given as Sn plus 1 equals T times Sn. So very familiar in terms of that recurrence relation notation. Complete the state matrix S0 below to show the number of planes expected to be parked at each location on Tuesday night. I think that's actually meant to be S1 there. And so we're asked to find S1 by doing our transition matrix. Okay, so our values from above that we were given, and multiply that by our initial state of 60 and 35. And that will give us our state at S1. So let's put that information in our calculator, and then we'll get our numbers of planes at each location. Okay, so I've just transferred that into our calculator there. And when we press enter, we will get, after one transition, we can see we've got 64.8 planes at Melbourne, 30.2 planes at Sydney. We will write down those decimal values, but then we will state our final answer. And that's where we'll do any rounding required. So 64.8, we would round that to 65 planes at Melbourne and 30 planes at Sydney. Much like we looked at previously with recurrence relations, we can also convert a recurrence relation into a general rule. And so that's what we have here with the state Sn. So any state after any number of transitions, we can find by doing our transition matrix to the power of that number of transitions times our initial state. So firstly, we need to be confident that we can convert our recurrence relation form into a general rule form. And so that's what we're being asked to do here. State the general rule for Sn using our movement of planes between Melbourne and Sydney. So Sn would be given as Tn. So our transition matrix, we actually do want to write out the values of the matrix, not just the letter T, to the power of n, and we would multiply that by our initial values, so 60 and 35. And so there's our general rule for that particular situation. We can then go on and use this rule now to help us jump sort of further ahead. So much like recurrence relations, remember, we can only use one state to get the next state. So if I wanted to find out if S0 represented Monday, what happens on Tuesday? It's after one transition. What happens on Wednesday? It's after another. On Thursday, after another. I would have to do that step by step. Whereas with the general rule, as long as I know how many transitions have occurred, how many times have I gone through this movement, I can use the rule to jump to the answer. So firstly, what we want to identify is find the number of planes expected to be parked at Melbourne on Thursday night. So firstly, think if S0 is Monday, to get to Thursday, we have had to go through 3 transitions. Okay? So Monday to Tuesday is 1, to Wednesday is 2, to Thursday is 3 transitions. So that means we are going to find S3. And we'll do that by doing our transition matrix to the power of 3 times our initial, and then we're able to get our matrix answer that we can then give our final answer from. Okay, so really important, I want you to be in the habit of writing your answer in a matrix form and then stating the answer to the question underneath that or beside that. Okay, so here in my calculator, I've got that transition matrix to the power of, and I was going to say to the power of 3 times my initial. When I press enter, I get my answer there. So I've got 66.8 planes at Melbourne, so that would be 67 planes at Melbourne, and 28.2, so 28 planes at Sydney. Okay, so as I said, stating your answer as a matrix form, and then giving the final answer of the number of planes at Melbourne being 67. For part E, find the number of planes expected this time to be parked at Sydney on Sunday night. So again, let's consider Sunday night would be from Monday, would be 6 transitions. And so that tells me that I'm going to find S6, which means my transition matrix to the power of 6 times my initial matrix, so always multiplied by that initial value. And when I do that on my calculator, I'm going to get 67.1 at Melbourne, 27.9 at Sydney, and so therefore I'll have 28 planes at Sydney on Sunday night. This next example is another VCAR question, but this time from an exam 1 multiple choice, but we're not giving you the answer options here. So a population of birds feed at 2 different locations, A and B, on an island. The change in the percentage of birds at each location from year to year can be determined from the transition matrix T below. And so looking at the transition matrix, we can see that if you were in location A this year, 80% of those birds would remain at location A in the following year, whereas 20% would move to location B. So just reminding yourself how to read that transition matrix. We're then told in 2018, 55% of the birds feed at location B. So that's giving us some information there about a starting point. So we can use that to help us with our initial matrix. We're then asked to find the percentage of birds that are expected to feed in location A in 2021. So if we're going to use 2018 as our initial starting point, then 2021 is going to be after 3 transitions. The second thing that we're going to use this initial value for is to create this initial matrix. So our initial matrix needs to be a column, location A and location B. Now, we aren't given a number of birds, but we're given a percentage, and I can use that. I can choose to use that as a whole number, so 55% were at location B, which means 45% must have been at location A. Or I could also write those as decimal versions because it is a percentage. Either way, you're going to end up with the same answer. It just matters how you interpret it. I tend to leave them as whole numbers because then I'm less likely to make a mistake there. Just be careful that you're using the correct unit. So here the percentage is my units. And so to build my calculation, if I'm finding S3, so after 3 transitions, that's going to be my transition matrix to the power of 3 and multiplied by my initial matrix. So in my calculator, I will put in my transition to the power of 3 and then my initial matrix as I've created it. When I do that, I get 65.3 at location A and 34.7 at location B. And so how many are expected, or what percentage are expected? Therefore, we can say 65% at location A. And so again, writing my matrix calculation, writing my answer in decimals, and then putting it back into the context of the question. And so in this case, they haven't stipulated whether you should round or not, but this would have been a multiple choice question. So you're giving the answer that's closest to location A, that's 65.3 that you found. This final example is a longer question. So this was from the VCAR 2018 exam 2, and this is question 3 from that. It's quite a long question, and so it's a really good one to show you of what you can expect in the exams. The High Roads Company has a contract to maintain and improve 2,700 kilometres of highway. Each year, sections of highway must be graded, resurfaced or sealed. The remaining highway will need no maintenance that year. So we can see those 4 options. Let SN be the state matrix that shows the highway matrix schedule for the nth year after 2018. The maintenance schedule for 2018 is shown below in the matrix 0. So there's our initial values. And remember, they're representing kilometres. So we had 700 kilometres graded, 400 resurfaced, 200 kilometres sealed, and 1,400 kilometres requiring no maintenance. The type of maintenance in each sections of the highways varies year to year, as shown in the transition matrix below. So here we can see all of that movement. And so a reminder that if I'm reading down and out, So we could see that 10% of the resurfacing would require resurfacing again the following year. Of the road that was graded in 1 year, 50% would require no maintenance the following year. The first question here, of the length of highway that was graded in 2018, how many kilometres are expected to be resurfaced the following year? So we're talking about going from graded to resurfaced. So from graded to resurfaced. So that is 10% of the original 700 kilometres that was graded that year. So of that 700 kilometres being graded. And so there we can say 10% of the 700. So that gives us 70 kilometres will require resurfacing the following year. The next part, show that the length of the highway that is to be graded in 2019 is 460 kilometres by writing the appropriate numbers in the box below. And so in this scenario, we're talking about all of the work funneling into and moving to grading in the following year. So we're going to have 20% of the graded road, 10% that was resurfaced will change to graded, nothing that was sealed will move to graded, and 20% that was no maintenance will require grading the following year. So make sure that the values in the that are already given, so the 700, 400, 200, 1,400, are in the order that are given in the state matrix, the initial state at the top. And then we can simply follow along and say, well, 20%, so 0.2 times 700, 10% from resurfacing, so 0.1, none of the sealing, and again 20%, so 0.2 times 1,400, and that will give us 460 as the answer there. We now have the state matrix describing the highway maintenance schedule for the nth year after 2018 is given by Sn plus 1 equals T times Sn, so in that recurrence relation form. Part C is asking us to complete the state matrix S1 below for the highway maintenance schedule of 2019, and that's after 1 year after 2018, so one transition. So let's put that into our calculator to get those remaining values. Okay, so we just have all of those values entered in there. So my transition matrix times S0 as given. When I hit enter, that'll give me S1. So I can see that the value 460 for graded and the 1,490 for no maintenance matches what is in the answer already. So I'll just fill in the final two values there. And so we have 390 kilometres for resurfacing, 360 kilometres for sealed. Part D, High Roads are looking to plan for their 2022 contract. How many kilometres of the highway is expected to require resurfacing in 2022? So firstly, let's think, how many transitions is that? So if S0 is 2018, that means we're going to have 4 transitions to get to 2022. So we're going to find S4. And so going to our general rule form, we know that S4 will be our transition matrix to the power of 4 times our initial matrix there. And that will give us all 4 of those values. And so that will give us our 4 values for each of the locations, so grading, resurface, seal, no maintenance, and from that we can then take out our value of resurfacing. So let's put that in our calculator. Okay, so I'm going to take what I already have entered in with my transition and S0 and do my transition to the power of 4 times my S0 matrix, and that gives me those values there. So I can see that graded would be 388, resurfaced would be 388.41 kilometres. And so again, I really encourage you to write that in the matrix form and then state your final answer. So if there was an error along the way, particularly because this is an exam 2 or something similar that you would get in the SAC, that you actually show your working in case there can be some follow through or consequential marks. Okay, the final part, part E. In 2020, 1,536 kilometres of highways is expected to require no maintenance. Of these kilometres, what percentage is expected to have had no maintenance in 2019? So first we need to think about what's happening to get from 2019 to 2020 in terms of our no maintenance. And so if we go back to our transition diagram, we can see that no maintenance looping around to no maintenance is 0.5. What we also have been given on the previous page is that in 2019, we had 1,000. So in 2019, we had 1,490 kilometres had no maintenance. So firstly, we can work out, well, how many kilometres? So 1490 times 0.5 meant that in 2020, we had 745 kilometres with no maintenance. What the question is asking is what percentage does this represent of the 1,536 kilometres in total in 2020. So to make it a percentage, 745 out of the 1,536 times it by 100, and we will get 48.5%. So 48.5% of the 2020 no maintenance was no maintenance required in 2019 as well. That's it for this section. Lots and lots of practice on transition matrices, because these are something that will come up again and again, and also in slightly different formats too.